We continue our discussion on design principles. In this part, we're going to talk about a few principles, three specifically, that are fairly fundamental to designing software. Let's start with the very first principle that I want to talk about, which is called the Yagni principle. We already talked about the Yagni principle in the session on evolutionary design and architecture, so I won't go into a lot of detail here. Please refer to that. But it's good to re-highlight and discuss this just to set the grounds about this particular principle, because one of the good principles to consider when designing software is the Yagni principle. I often use it with a slight twist. Rather than saying Yagni, I normally say Yagni Y, meaning you aren't going to need it yet. And this principle is something that I use quite often when I'm starting to design software. This really helps me to postpone certain decisions that I don't need to look at the moment. So by postponing a certain decisions, it really gives an opportunity for us to keep the focus on the area, a smaller area that we want to really focus on, and not have to worry about some of the details that can be done a little later. And potentially going this route, we may even realize some of the abstractions we plan to implement are no longer needed in our case. Now, this is one of the things that I'm going to say, at least this is true with respect to the restaurants here in the US, that restaurants feed us a lot more food than we should really be eating if we are concerned to be healthy. They feed like there is no tomorrow. Much like that, a lot of programmers write more code than they should really be writing. A good restaurant serves a right proportion. A good programmer writes to the right proportion as well. So when we realize a particular code may not really be needed, if we can postpone implementing it until we learn better, then we can decide whether we really need it, or we can get rid of it because our solution really doesn't need it, even though we thought that's really needed. Again, like I said, we talked about this quite a bit in our discussion in the Creating Evolutionary Design and Architecture. I suggest that you take a look at that about the Yagni principle. But Yagni principle comes in really nicely to minimize the amount of code and keep the design lightweight and maintainable as well. And I really like this principle quite a bit. But of course, we got to balance this principle and really think about extensibility as well. We cannot completely discard it, but we have to really apply that in the right measure to the right proportion. The next principle I want to talk about here is one of my most favorite principles. It's called the DRIVE principle. The DRIVE principle stands for don't repeat yourself. And it says every piece of knowledge must have a single, unambiguous, authoritative representation within a system. So this says it's not just about duplication of code, it's about duplication of effort as well. So we all know about duplication of code, copied and pasted code. We all have seen it, we all have done it. I was programming a system a few months ago, and I was implementing a certain feature, and within a matter of about 5 minutes, I had the feature working, and I stopped and I asked myself, how did I get that done so quickly? And I went in to examine, and without even realizing I had copied and pasted code and got it working. I felt really ashamed of myself, but that's very natural for us to do. We copy and paste code quite a bit, but once you realize it, it's important for us to go back and refactor the code and remove that duplication. If we lead to duplication of code, it really becomes expensive to fix the code and evolve it as time goes on. I remember once running into a programmer and he said, well, every 2 months we fix the same bugs. I said, oh my gosh, is somebody really putting bugs back into the system? He said, no, every few months we discover that the same buggy code has been copied and pasted elsewhere, and when we find it, we go fix the error. I asked, well, when you do find this and fix the error, you refactor and remove the duplication, right? He thought for a minute and said, yeah, that's a great idea. We should start doing it. There is no way we can get better if we keep the duplicated code. We definitely have to refactor and remove the duplication. There are tools available like PMD, for example, copy-paste detector, that looks for code and finds out where there is copied and pasted code, and we can use such tools to really find duplicated code. But it's not just about duplication of code. Duplication of code is a violation of DRIVE but not all violation of dry is duplication of code. So you could be violating dry without duplicating code. It's duplication of effort. I've got another video where I show how to really use dry with an example in Grails. I highly recommend you take a look at that video for a real example of dry in terms of effort. But let's go ahead and talk a little bit more about the dry principle. This is often seen as one of the most difficult principles because it slips by, like I said, quite a few times. But let's look at some concepts here. Well, it's sometimes very hard to realize we are violating the dry principle, and we often end up copying and pasting and duplicating code. But the more duplicated code we have, the more expensive it is to maintain the code I mentioned. I remember teaching a course on a technology a while ago, and as I was showing how to really do validation in the UI, by writing a component called the validator and then sending a message to it. It took about 10-15 minutes to write this code. As I was showing this example, a really good developer raised his hand and he said, "Hey Venkat, I've got a question for you. You are writing this component called the validator, and I saw you spend the last 10 minutes or so writing this code, but I want you to go back to the IDE and go double click on the form. Look at the property page. Right there, you have a little button called validate. Click on that button. Right there, you can type the validation logic, and you are done within about 5 seconds to 10 seconds. Why in the world would you spend 10 minutes writing something when I can just do that in about 10 seconds? Very good question. And I said, you're absolutely right. But imagine now this field is in 40 to 50 places in your application. How are you going to go perform those validations? And when a logic changes, you got to hunt every place and change it. He laughed and he said, well, there's a reason I asked this, because I wish you had told me this a few weeks ago, because I had done exactly that. And last weekend they changed the validation rules on us. And guess who was here at work on Saturday hunting down all the forms and fixing it? I dread it, and I wish I had done it this way before. Yes, it would have been 10 minutes of extra effort, but that is a lot more extensible and maintainable. So that is something important. And I learned the lesson the hard way myself, and I'll give you an example of that in just a few minutes. So essentially, the idea behind the dry principle is we have to make sure that we don't violate this duplication everywhere. In an engineering application that I was working with, what I had done was we had a simulation engine, and then we had a UI that was sending the data to the simulator, letting the simulator run and pull the data and display the results. We found that there was a bug in the simulator that it would crash when a certain type of data was being sent. Well, we couldn't fix the bug on a timely manner, so again, they say the pathway to hell is created on good intentions. With a desire to make this better, what I had actually done is I had fixed the UI so that this particular data that wouldn't be valid is not sent to the engine. Well, about 6 months went by. One of the engineers got down to the simulator and fixed the bug. As soon as he fixed the bug, he starts the application, tries to enter the data that was not a good data in the past, and the UI immediately blocked and said, no, I'm not going to let you pass that through because that's not a valid value for the simulator. Well, immediately he reported a bug and said, well, you got to fix it. The UI should be able to send this. Well, I fixed it, and within a few days, he reported again, and within a few days, he reports in again, and eventually I realized that in my desire to prevent the simulator from crashing, every single place this field was being used in the UI, I had duplicated the logic. Shame on me, but that's what I had done without thinking. But this time around, I realized my error, realized my mistake, and I created a component for validation, and that's where I learned that it's better to really create this little component, and every place where validation is needed, it should better call into this logic. Then there is one place to make a change rather than several places to make the change. And that's what it really boils down to. Every piece of knowledge in the system must have a single, unambiguous, authoritative representation. In the case of validation, that validator is the authoritative representation. Now, likewise, when you're creating an application, don't try to do the same thing in multiple places. Now this is easy to argue, and then we can say, well, what if I need to do client-side and server-side validation? You see, on the server side, I would have to write code in one language. On the client side, most likely got to do JavaScript. Aha, now I have to duplicate that, isn't it? Because my languages are different. Well, only if we want to. But if we put in a little bit of an effort, we can do code generation possibly in those cases, or find a way to do a common representation and pull the code out of that for the validations, and so we don't have to duplicate the effort. So we have to really put in some effort to really remove the duplication because it's so easy to end up duplicating. Now, one of the things I realized over time is that when I was developing a certain application, I had taken the time to really refactor and remove the duplication. About 1.5 years later, I came back to add a feature to the application, and that just snuck into the place, and I was able to reuse the code. And I thanked myself at that time because it was so easy to implement, because that's one example where thankfully I had done it right way. So it's important to really remove duplication and follow the dry principle. That's very, very important. Now the opposite of dry, of course, is wet, and somebody said wet stands for write every time, and of course you're going to duplicate and write every time you don't want to do. Other acronyms are called DIE, D-I-E, which stands for duplication is evil. So there are different acronyms floating around by different groups, but dry principle was popularized by the pragmatic programmers in the famous Pragmatic Programmer book, and this is one of my favorite principles like talked about. The next principle I want to talk about is the single responsibility principle. Another name for this principle is cohesion. We want everything to be having a single narrow focus and do one thing and one thing well, and this is an extremely important principle to follow. So what is the metric that comes to mind? Cohesion, of course. A class must have one single reason to change. Well, back in time when I was programming in C++, I would come across often with C++ books where they would show how to overload an input and output operator, and that I consider to be very evil. Now, if you're going to be doing I/O-related operation in every single class, it really becomes coupled with your system. It becomes really hard to change the way you represent it. So if you decide not to use a terminal and build a UI, it becomes incredibly difficult to extend it. So that separation is extremely important. Let's revisit this with a little bit of an example. Let's say in the top design here, I have an alarm. And notice I have an alert method on the alarm, but I also have a display method on the alarm as well. While the display is depending on the panel, you can see the coupling slowly creeping in here. The alarm's UI, of course, is displaying the alarm. If an alarm goes off, the visual alarm is displayed in the UI, whereas a control system is the one that's going to generate a threshold condition that the alarm is going to go trigger. Well, the problem in this code is, look at the alarm for a minute at the top. The alarm in the top fails the single responsibility principle. It's responsible for alerting, but it's also responsible for displaying the information as well, and there is too much going on in this code. If you decide to change what it's going to alert, this alarm has to change. If you decide to change how to really do the display, if your UI mechanism is going to change, that's going to affect this as well. On the other hand, let's apply some very basic principle of control entity and boundary objects. A control object is an object that really does algorithm and logic, works with multiple other objects. An entity is a holder of data, and a boundary is the view. So you could think about this as MVC. Here is the model right in the middle. C is the control, and the view, of course, right here is the boundary. Now, the beauty of having these three different things is you can change the view independent of the logic, and you can change the data representation also independent of the logic. And on the same data representation, you can introduce other pieces of algorithms and logic, so you can see how it nicely gives you a way to flex. So in a sense, what this gives you is this ability for different parts to really flex themselves. If they were all too tightly coupled, and that would break, and whereas here it's nicely flexible because one can change independent of the other, and that gives us the freedom to change. Coming back to this example here, notice our alarm now only has an alert, and the control system now can send the alerts to the alarm. but the UI is separated. Now you can change the UI entirely and come up with a completely different UI that doesn't affect the alarm at all. So this nice separation, and each of these are very focused, narrow. You want to apply cohesion or single responsibility principle at component level, module level, function level, and so on. So that becomes extremely critical. Now here's a way to think about cohesion or single responsibility. When I was a young brat, I would come from school and eager to go out and play. I would throw things into my room and run away. And when you open up my door, there'll be a pile of things piled up. There is books and there is clothes and there are other lot of different things and toys and devices, everything jumbled up together. And if I'm in a rush and I want something, if I get a red sock, I could not find the other red sock, and it would be really a chore to go find what I need. Well, that's a lack of cohesion, lack of single responsibility. Everything is piled up together. A lot of times we write code like that, where you open a code and everything is happening right there. You talk to database, you perform computation, you do XML parsing, you do JSON parsing, you do a lot of stuff in this one class. My gosh, what's going on in this one class? It lacks single responsibility. Instead, back to my example, now I have a drawer where I have sock. And colored sock in one drawer, different colors grouped together. If I want blue sock, I know where they are. If I want red sock, where they are. And my clothes are far away from my books. And similarly, my kitchen utensils are far away from the books and the clothes and nicely kept. That is cohesion. If I walk into the kitchen, I would find utensils, not my sock, obviously. And likewise, if I walk into my bookshelf, into my study, I'm going to see my books and not my utensils or my socks for that matter. So that's a separation of concern, and we have single responsibility for each of these holders. Likewise, at the code level, this class deals with the logic, not XML parsing or JSON parsing or writing to the database or creating the UI. And this does only the logic over here. It calls this function, which then communicates with the remote service, gets the data and parses it. Then it sends the data to this other class, which will display the data in the UI. Tomorrow, if I decide to change the UI or the display format, rest of the code is not affected. This can change. Also, if I decide not to use JSON, but use some other format for data, that component that deals with data parsing will change, and we can substitute that, but rest of the application is not affected. That's single responsibility principle. So as you start designing system, do not put in one place where what belongs elsewhere. So ask yourselves, what's my primary purpose here? If my primary purpose is to do this logic, I should only keep to this logic. Anything that this needs should be separated into another class or another function, and that can focus on that separately. That reduces complexity in the system. That decreases opacity in the system. That increases reusability in the system. That makes it less fragile. Notice how this single responsibility principle can contribute to easing the smells we talked about in previous parts of this presentation. So a single responsibility principle is an extremely vital principle. By applying single responsibility principle, we can make the code a lot better in several of the design areas. It becomes less fragile, it becomes more mobile, it becomes reusable, it is easier to understand, it reduces the opacity, makes the code transparent, and all that benefit I talked about comes in very, very handy here. Now, not only is this important at the class level, we got to take care of this at the component level as well. This is something that comes to mind way back in time. Microsoft had something called MFC, which was a GUI library, graphical user interface library. Back in time when they introduced COM, they didn't really have a way to really do COM in C++ much at that time. They were really low-level classes, really had a better set of tools. So they came up with this little thing called C command target. That was a one small class. Where do you put that one little class? Well, they decided we're going to stick that into the GUI framework. And all of a sudden, their GUI framework was shipping with a component, a little class that didn't have anything to do with the GUI. It was really for distributed computing. But if you wanted to use that little feature, you had to download MFC. That's like saying, I'm really interested in this little fly, but I got to bring in the elephant whose tail has that little fly sitting on it. Well, unfortunately, this was lack of cohesion at the component level. So when you design software components, ask yourselves what classes should be in this component. If this component is mostly dedicated to database interaction, then make sure that the classes are belonging to that. If this is component that's dealing with UI, make sure it really focuses on that. If this component is dealing with security, make sure all the classes there work towards security. If this component is really dealing with XML parsing, make sure all the classes there contribute to that and keep them separate. Think of the example, kitchen utilities versus books, and you don't want to put one in the other place. Yes, of course, it's so convenient to be sitting in the study and eating, but you don't want to leave dirty dishes there. You want them back in the kitchen sink. So the point really is that separation of concern at the component level is very important. Eventually, of course, Microsoft created ATL library, which was completely for COM, very small library, relatively speaking, but didn't have anything to do with the MFC, and that was a nice separation of concern. And we should really strive to do this. There are very many other examples we can think of. So when you have a low cohesion, it really results in poor reuse. Low cohesion is where we are failing on single responsibility and our code takes multiple different responsibilities. And so, for example, let's say my brother has bought a new DVD player and a big screen TV, and he says, you know what, I don't need this VCR. Of course, VCRs nobody needs anymore, but he says, I don't need this device, you can take it. Well, when I go over to pick it up, I realize that VCR, you probably remember those units, is surgically attached to a TV unit. I'm sure you have seen your versions of those, right? There's a TV, and along with it comes a VCR attached to it. Now, what if one breaks and the other one is good? How do you use it? Hey, the VCR is broken. Oh yeah, we got another VCR, but that TV is what we're going to use. It's even worse. What if the TV is broken and the VCR is working now? Where do you put that little VCR? On top of the big screen TV? So the point really is, that is an example of cohesion gone wrong. And if you ask that unit, what does this do? Oh, it does give you TV and, well, that and reveals the problem. It is doing too many things. It is very tight coupling of two distinctive things put together, and also it's very poor cohesion and ends up with a bad reuse. Now, at a device level, we see this all the time. In today's world, where we have smart devices, smartphones, and it can be, and in fact, a smartphone is anything but a phone, isn't it? So we have this kind of lack of cohesion where devices tend to do too many things. Like one of my favorite appliances at home is a clock radio. It's got a nice little clock and I love it, and it's got a radio on it and I can listen to the radio, I can set an alarm on it. So you could argue you don't have a separate alarm, you don't have a separate clock, you don't have a separate radio, all of that is in one. Is that really wrong? Well, that's really an application level thing. But at a component level, software doesn't really translate the analogy because it becomes really hard to maintain if a piece of class or a software that is doing too many things. So we should really put them together into a combination, but each of these parts must be very cohesive and they should come together to do what we want. Otherwise, it becomes extremely difficult to maintain this code. It becomes hard to evolve this application as well, and it results in the smells we talked about. So when it comes to software, every class you write, every function you write, you ask yourselves, what's the main responsibility of this class? And immediately clarity emerges out. Oh, if the main responsibility of this class is to do this, I know it needs this, but I wouldn't do this operation here. I will delegate that to another class and I will focus on the core behavior here. And if you start asking this question, what's your primary responsibility? You will see that the code becomes more cohesive, becomes narrow, focused, and well, really intended. And then it becomes easy to modify parts of the application and evolve it. So single responsibility principle is a very, very important principle to follow when it comes to developing software. That is something we cannot just take lightly. So we talked about the single responsibility principle. Next, we're going to get to some extremely important set of principles, namely the open-closed principle, and we will get to that next in the next part of this presentation.